everyone, and today we are presenting safeguarding UEFI ecosystem. A firmware supply chain is hard-coded. I'm Alex Matrosov, and I'm presenting today with Alex Teryshkin and Adam Zabrodsky. We are offensive security research at NVIDIA, part of NVIDIA product security team. I will be save time on discussing our BIOS and focus on our today agenda. Actually, I will be touch our motivation of this research. Also, my part is about complexity of UEFI ecosystem, and at the end I will be discussing two bugs we discovered with Alex Teryshkin at Dell Power Edge Systems. Alex will be discussing Intel reference code vulnerabilities and pre-initialization stage, and you will be see the sweet demo where our payload it survived from platform initialization phase, choose Dixie, SMM, and attacking operating system level. Adam will be focused on mitigations, or mostly lack of mitigations at system firmware, runtime, and also we'll be discussing very interesting bug in EDK2 platform, and of course summarize our research today. So what is the motivation of our research? Actually, we found all the bugs during our internal assessment, and honestly, complexity of modern firmwares, it's just growing with every release, and numbers of code, it's just increasing. Actually, if you think about modern security solutions, it's just mostly focusing on operating system level, and not much technologies exist to track the threats below the operating system, right? So, and it looks like an iceberg, and most of the security solutions just see the tip of the iceberg, but this underwater layer, which is very complex and dangerous, it's behind the radars of security solutions. And actually it was a very interesting presentation done by DHS CISA in the recent RSA conference, where they've been discussing the complexity of ecosystem and a lot of other things, but most important thing, it's need to be regulated, and of course vendors need to be adopt more mitigations and security practices of developing the firmwares too. If you think about the mitigations, actually Microsoft and Intel doing the good job on it, and but not all the vendors actually following the best practices. And some of the vendors actually claiming they are use mitigations, like on this screenshot discovered by Asaf. But Windows SMM security mitigation table, which is actually filling up during runtime boot phase, sometimes having the true value on the mitigations, but vendor doesn't use it. So basically, without enforcement and control, that doesn't work. Also remember good old days of attacking BIOS. Alex and Rafael in 2009 been presenting very interesting bug in decompression during the platform initialization phase with complementary unprotected metadata. It's been in the BIOS image, it's been lead code execution, controllable code execution, and the payload been survived to the SMM. We found very not similar, but we will also targeted platform initialization stage on Alex part, and you can see very sweet demo as we did in 2021. So it's a lot of year past, but we still having these problems. Let's talk about UEFI ecosystem and complexity of it. Actually, Tremel Hudson did a very good job of describing this complexity of ecosystem during his keynote in 2019. But look on this picture where we have Intel AMD, which is basically designing the reference code, and this reference code get adopted by frameworks like Phoenix, Insyde, and American Megatrends, and used by device manufacturers. And honestly, it's not much code developed by device manufacturers. Usually it's just 5 to 7% of from all the code base. And the vulnerabilities which can be found in Intel or AMD reference code if this code gets used. So it's basically the impact mostly always on the whole ecosystem, right? Same thing about Phoenix, Insyde, or Megatrends frameworks. If the bug found in their code, it's impacting their full ecosystems. And this is very dangerous. But Apple and actually Microsoft with Surfaces pick the different way they try to develop their firmwares, and they just adopting Intel and AMD reference code, which is good. And Apple switching from the x86 to ARMs, which is very interesting way of developing the firmwares, and not covered in our today's presentation. So nvram variables access during boot flow, because we will be discussing how it can be dangerous on the following slides with the vulnerabilities. So basically, let's talk about nvram persistent storage, right? So this storage, it is nvram part existent spy flash, and can be potentially accessed by the attacker with the physical access, right? So these nvram variables can be used by platform initialization phase and Dixie phase. And actually, if we have nvram runtime variables, it can be changed during the boot. But nvram persistent storage, it's actually persist on the spy flash, and vulnerabilities lead by this data can be very dangerous, because it can be gain persistence for the attacker, right? So, but also let's touch a bit our attacker model. So we are not talking about remote vulnerabilities, it is local attacker, but all these vulnerabilities can be combined with remote chain of exploitation, and attacker can gain privileged access to the operating system, trigger the vulnerability in system firmware, and gain access to the system management mode, and impact virtual machines, guests too, and bare metal clouds deployments. So what is nvram persistent storage? And actually, this screenshot from UEFI tool, it's demonstrating this region actually doesn't cover it by boot guard. That's mean secure boot doesn't protect this region, and also it can be abused by the attacker with the physical access, right? So basically, if the attacker can modify the storage, and this data can lead code execution during the PI or Dixie phase, it can be very dangerous vulnerability, which is allows the attacker to gain persistence, right? So, and arbitrary code execution in the get variable, unfortunately, not rare. And we will be discussing some of them today during the next part of our presentation. And if the attacker can modify nvram persistent storage, also it can lead some fileless Dixie SMMPay implant shellcode, which doesn't exist on the Dixie volume or pay volume. It's just led by nvram persistent storage shellcode, or like some malformed data in it. What is our methodology? We heavily use IDA during our reverse engineering, as well as UEFI Code Explorer plugin. And actually, UEFI Explorer plugin can help you to navigate on UEFI code, because it's reconstruct a lot of data. And actually, this plugin we already presented on Black Hat Europe last year. But most interesting thing, we add functionality for finding the get variable bugs during the PI and Dixie phase automatically. Of course, we don't guarantee 100% of the coverage, but it's good tool for validate your firmwares. Let's discuss two sweet bugs we found on the Dell Power H systems. One of them, it is classical heap overflow, and another is classical stack overflow. So that's the story of two buffer overflows. And first one is very interesting, because a mistake in variable parsing leads a heap overflow, and as a result, the code execution cannot allow the attacker to execute controllable payload. So basically, we have EP variable, an nvram, controlled by attacker, and buffer for erase record share allocated at the heap. So basically, during the execution, this cycle after the second try can lead the heap corruption, because if the length bigger than 964 bytes. So this bug we found in the Crystal Reach, and it's been part of Dell advisory DSA 2021-103. We found with Alex Teryshkin, it's already public, but also interesting detail, the payload is not measured by TPM PCRs, and remote health attestation will not detect the exploitation. So another bug, it's in mirror request nvram variable. And this bug is actually very interesting because we have two advisories for it. One on Intel end, because it's targeting Intel code, and second, it is on the Dell, and where we found this during internal assessment on PowerEdge server. So basically, this bug, it is a classical stack overflow, because subsequent memset will override platform initialization stage with zeros during the PI phase, and mirror request length, if it is bigger than 5, as you can see, the data size is hard-coded. So the attacker can control the length, override the buffer, can modify the parts of the save at return address, and control execution flow, which may lead arbitrary code execution on the platform initialization stage. And this bug we found in Encore PM, platform initialization driver model, and this exactly model actually point us to two different other bugs, which will be Alex discussing in the next part. And actually, this payload also not measured by TPM PCRs, and remote health attestation will not detect this exploitation. But Microsoft did very good job with Windows 11 to push the industry of use TPM, and of course it's actually very good initiative to increase the assurance for secure boot and DRTM boot flows. Okay, I will be passing the stage to the Alex, and he will be discussing very interesting bugs in Intel reference code.
Thanks, Alex. Now let's talk about PEI initialization phase, which is pre-UEFI initialization phase, and the way it accesses and handles nvram variables. Of course, PEI code heavily relies on nvram variables because all the configuration data for BIOS is stored there, and this is why UEFI variables are a good attack surface for PEI code as well. The way these variables are read from the nvram is similar to DXC phase. There is an interface for that, which is called getVariable, and the prototype is very similar to getVariable call for DXC code. So the same mistakes can be made for PEI code as for DXC code. For example, let's see at this code, which runs in Encore init PM module for PEI phase. It runs on Grantley and Perley systems. So let's see what is wrong here. So first of all, getVariable call returns status, so it may fail, but there is no status check in this code. So for example, the code may return status buffer too small, and that happens if the data size provided to the getVariable is not enough to contain all the data which is read from nvram. So in this case, getVariable fails, and data size will return the actual size of the variable that is going to be read. But anyways, the code continues and allocates this number of bytes, which can be large, up to the size of nvram, for example, and allocates a pool of that size. Again, there is no check if this allocate pool succeeds or not, so it may fail and return 0. But after that, memcopy operation will continue and just copy some stack data to this freshly allocated buffer. So when you see code like this, that means that the developer may have made some more mistakes. And let's see what comes next. So continuing with the same Encore module, the same Gruntly and Perly systems, we will see that there are multiple problems besides the one that we talked about. For example, it's very dangerous to call getVariable code in a API in a loop, because if you don't set data size immediately before getVariable, it may reuse the old value from the previous getVariable call, and this may be controlled by attacker. So this code shown in the picture, it reads a chain of UEFI variables. So then each next variable contains the name of the next variable in the chain in the beginning of the data. So this code parses this chain, but it does not set data size value to immediately before running getVariable API. So data size on the second iteration of the loop may be large and controlled by attacker actually. And next time getVariable executes, this API will assume that the past buffer, which is next chunk name and data in the slide, the size of this buffer is large, and it actually may be set here that it is larger than its actual size on the stack, because again data size is controlled by an attacker. And this API will just overwrite the stack because chunk name buffer is allocated on stack, and there you have it. This is a stack buffer overflow. So there is no ASLR or cookies in the PI code, and it's just very easy to exploit this kind of vulnerability here. So, but what is interesting is that we don't even need to exploit this vulnerability that we found just now in this PI code, because there is a feature that is implemented in this code that actually is designed to run arbitrary unsigned code read from these UEFI variables. Let's see how it is implemented. And yes, this is reference code from Intel for Perly and Gruntly systems. So this is the snippet of the code that reads this chain of variables starting from variable tool H and builds a contiguous 32-bit portable executable image. So here, this is evload tool is a function that parses this chain of variables read directly from nvram and just reads the data from there, builds a buffer, fixes relocation, and executes its entry point as entry point for portable executable module. So as you see here, there is no extension of any PCRs and TPM, so there is no validation of any signature. It's just some unsigned code that is loaded from UEFI variables and executed. So of course remote attestation also will not detect this exploitation, because again PCR is not extended to this code. So you may think, what is the purpose of this feature? This was actually intended for manufacturing, debugging, or testing purposes. And there is an Intel guidance for this feature, which they tell to IBVs that this feature is not supposed to be enabled on if physical presence has not been established. So BIOS vendors are supposed to implement this code that would check if there is a physical presence at the actual box before launching this unsigned code. But not many OEMs obviously know about that this feature exists, and it may be enabled anyways. So if this feature actually is not used by OEMs, it should be disabled. That was the guidelines from Intel. But this is what implementation looks like in the Intel reference code. So Intel left this function for establishing physical presence as an example to IBVs, how they can implement it. And this is just a Boolean function that returns true all the time. There is no any checks. IBVs should implement these checks, but again, this is an example from reference code, and it returns true no matter is there any presence or not. So not all BIOS vendors are oblivious to guidelines, and for example, Dell fixed this vulnerability in their own code, and just removed the setup knob feature so that this feature could not be enabled and the code just could not be reached because there is no status knob, setup knob that controls this feature. But there are many other vendors that ignored the guidelines and reused the original reference implementation code without introducing any changes to it. So it's clear that Intel should have put return false in this default implementation so that this implementation could be reused by every vendors, but instead they returned true. So this code that reads the unsigned data and executes it as a code is available to any actually any state of the machine, whether physical presence is established or not. So yeah, again, reference implementation can be actually de facto implementations. So this is why proper care should be taken, and the defaults should be very secure. Otherwise, the code may be reused without even taking care about what it is in this code. This is the official Intel's response that was provided to us. So they say that BSSA, this is the name of the feature, is designed for manufacturing feature, and it is only intended to be used on manufacturing lines. So Intel has provided the guidelines to IBVs about this feature, but again, not every vendor followed the guidelines. Let's look up the details about this feature. For example, how can you get the name of this feature, because there is no reference to the name of it in the code. So there is a GUID which is used to read the nvram variables that contain this code in UEFI variables. So when you Google this GUID, you get a link to this EDK2 discussion page. So you can know the GUID name from that page. And when you continue investigation, you can find that certain details to this feature is called system agent. That's probably the SA, the first two letters from this feature name. And this is how the payload is probably called. When you dig the details a bit more, you can find the references to BSSA feature all over the place. For example, this is a screenshot which can be found on the internet, a screenshot of some BIOS settings, and you see that some BIOSes implement this knob for disabling or enable this feature, which can be manipulated by an attacker also. But what is interesting here is the timestamp on the top, and you see that this feature was available since at least 2016. And there are certain implementation details that you can also find on the internet. For example, the number of postcode, which is related to this feature, which is also used in the code. This is let's discuss a bit the payload that you can implement and which can be run using this vulnerability. So you get the execution in PEI phase. So what can you do? You must survive the transition between PEI and DXE phase, which is a transition between 32-bit and 64-bit code, and then you will have to jump to SMM mode. And you can do this by hooking certain APIs from DXE core. For example, you can jump from PEI to DXE using hooks for DXE core locate protocol. Then you can wait for SMM core to be loaded and then hook SMM locate protocol there and just install software SMI handler at the end. So this is how you can gain this execution in SMM code when the system is already booted. Let me show you the demo of the real attack that we implemented. This is an output of our payload. You see here that it survived the transition between PEI and DXE. Then it hooked SMM locate protocol function and survived transition between DXE exit boot services and operating system load, and then it establishes its software SMI hook. And on each software SMI that it catches, it scans the memory for, let's say, secrets. For example, keys. This is how you can scan the memory. You just, on each SMI, you just scan a certain portion of the memory and just iterate through physical memory. And for example, here you can see that the code located some private key in the memory. Then it's up to the code to actually exfiltrate this data. Okay, I pass the control to Adam, who will talk about safeguarding UEFI ecosystem. Thank you.
Thanks, Alex. My name is Adam, and in this part of the presentation, I would like to speak more about safeguarding UEFI ecosystem. However, before we move there, I would want to briefly talk about FE development kit known as EDK2. And by EDK2, I mean I would like to spend some time and to describe one of the vulnerability which we found during our research, which has assigned CVE number 2021-28216. However, what is EDK2 FE Development Kit? It's an open source implementation of the Unified Extensible Firmware Interface known as UEFI, which is supported by the community and especially backed by the Tiano core. And EDK2 is advertised as a modern, feature-rich cross-platform firmware development environment for the UEFI and UEFI platform utilization specification known as PI. And what is cool, EDK2 supports tons of the platform, including Intel, AMD, ARM, Ampere, HiSilicon, BeagleBoard, Marvell, Raspberry Pi, RISC-V, and many more. Which is very interesting because it's open source and everybody can go, take it, recompile it, and just run on their own platform. But there is cost for that, because it runs on so many platforms, supports so many interesting environment. Essentially, any bug which could be found them could affect all of them, which means that one bug to rule them all, to rule all of the platforms. So it's very interesting and portable, but at the same time very interesting and dangerous from the attacker's perspective, because it's a very juicy portion of the software which could be attacked by the attacker and affects multiple platforms. And an example of such vulnerability could be exactly the one which we found during our research with the CVE number 2021-28216. So that's the code of this vulnerability function where the vulnerability exists. I know it doesn't look pretty, and I will try to make it much more digestible and walk step by step what we can see here. This is code essentially in the portion of the UEFI responsible for the S3. At first, I mark on the green the performance variable, which is read from the nvram, and nvram could be modified by the attacker during the runtime. And this variable is being read using API get variable, so it's fully controllable by the attacker. And next, a performance variable is extracted. It's cast as a structure, and some value from the structure is extracted and is being assigned to the new temporary variable marked here on the blue boot performance table. Next, the boot performance table is used to calculate a pointer, firmware performance table pointer, which is marked here on the orange. So essentially, firmware performance table pointer is also fully controllable by the attacker. And on the right, we see the while loop. While loop runs until the GUID is not null, so it can run multiple times. And essentially, what we can see in this loop on the right, we could have the arbitrary override vulnerability, because firmware performance table pointer is never validated and is fully controllable by the attacker, and the copy mem try to store some data there, firmware performance data, essentially. And we can overwrite any portion of the memory which attacker fully controls. And however, the story doesn't end here, because next on the bottom of the loop we can see that firmware performance table pointer is modified and some elements is added to the value of that. So essentially, firmware performance table pointer can change the value every time when the while loop runs. And on the bottom, on the right portion of the slide, we see that the blue middle variable, which is also fully controllable by the attacker, boot performance table, is extracted, some structure from there, and it's modified the value of the length header using the exactly previously modified firmware performance table pointer, which is subtracted from the boot performance table. Essentially, we can see here a semi-controllable write whatever vulnerability, because boot performance table is fully controllable by the attacker, and firmware performance table pointer is also semi-controllable by the attacker. So we have semi-controllable write whatever vulnerability, which is one of the most dangerous types of debugs in the software which you can get, which is very, very interesting from the attacker perspective. And even more, the exploit, when you try to exploit such vulnerability, the payload which you inject will not be measured by any TPM, and none of the TPM PCR will be extended by this payload. So essentially, remote health attestation will not detect the exploitation of that specific bug, which is very interesting and attractive from the attacker's perspective. However, vulnerabilities which we discuss, like during this research, this presentation, is one thing, and another thing is how easy to exploit them. So let's briefly talk about mitigation and hardening below the S. What the current state of the mitigation and hardening? Are there any technologies who makes the cost of exploitation higher? Is it even possible to exploit such kind of vulnerabilities? And I think this is the great slide which is taken from this year's presentation from RSA 2021 made by the Boyden and Thomas, which they essentially also focus on that problem. And I think this slide is great, and that's why we quote it here. So what we can read here, that the popularity of the UEFI and lack of various memory protection enforcement attracts exploitation. Essentially, there is a few bad news here. Like one, there is no way to apply some of the mitigation in the below the OS, and the example could be SLR. It's kind of standard mitigation in the OS world since around 2005. However, there is no even target date when such kind of mitigation could be adopted in the UEFI ecosystem. We don't even know if it's even possible in the current state to adopt such mitigation in the UEFI. And because of that, we can see that there are also more criminal and advanced threat actors starting to exploit vulnerabilities below the OS that affects UEFI ecosystem, because it's just easier than do some kind of exploitability in the OS. And also, as you know, one bug to rule them all, it's also much more beneficial to exploit bugs in the UEFI. And there is also lack of various existing memory protection, like non-executable memory, from various reasons, which is pretty bad state. So we went one step forward and starting to read about EDK2 documentation, what they have, any kind of information about the current mitigation technologies which could be enabled there. And essentially we found this interesting table here, which essentially summarizes various technologies which could be enabled or not enabled in the EDK2. In the blue, we have all of the mitigation which could be enabled in the production, so they are designed to work in the production. In the yellow, we have this feature which are not targeted in the production image. They are mostly developed for the debug as a debug feature and could be used in the development phase, but they are not recommended and we should never enable them in the production. However, some of the mitigation are not compatible to each other. For example, SMM static paging are not compatible with the heap guard. And also SMM profile mitigation are not compatible with the static paging as well. So essentially, even some of the mitigation exists, we need to very carefully analyze which of the mitigation could be enabled and are compatible to each other. However, what is the trick here? That all of these mitigation are not mandatory. This is description that they might be enabled, but they are not mandatory to be enabled. And moreover, if you go forward and starting to read about the various technologies, mitigation technologies in the documentation, you find pretty interesting information. For example, when you read about the stack canary mitigation, it says it could be enabled, however, it is disabled by default. So it's very unlikely that any vendor will go and change the default behavior of the stack canary mitigation, and most likely it's going to be left in the default value, which is disabled. If you read about non-executable memory, it also says it might be enabled to mark some portion of the memory like stack to be non-executable. However, it might. It's not mandatory, and it's not like that by default. So by default, the non-executable memory mitigation are not enabled. ASLR IDK2 does not support ASLR at all. And some of the pretty easy bugs like null pointer and reference could be easily mitigated. However, if you read about the documentation about that, we read that the current UEFI firmware always map the 0 page. So essentially this mitigation is not enabled as well. So the state of the current mitigation doesn't look great because all of them are not enabled by default or just does not exist or are not supported. However, there is also additionally to that a limitation to this mitigation, and if you poke more about the documentation, this is what you can find. That, for example, the pre-EFI initialization phase known as PAY does not support any kind of the mitigation based on the guard paging. There is also interesting that they, in the same time, in the same chapter, they write that there is no technical reason to not enable them. So technically they could be enabled, like stack guard or heap guard or null pointer detection. However, they do not support such mitigation in the pay phase, even there is no technical reason to not do so. Also, some of the mitigation like heap guard feature could increase the memory consumption and may cause memory out of the resources, especially in the SMM mode. And because of that, many vendors just don't want to have such problem and never enable mitigation like that because it's problematic for them. Even more, these vendors who try to enable some of the various mitigation technologies, they test and they see significant performance downgrade. This is what they observe, and because of that, they don't want to enable them. And also, some of the mitigation are not compatible to each other. Example, if you enable the heap pull overflow detection, you cannot enable at the same time underflow detection and overflow detection in the one image. You must choose or underflow detection or overflow. You cannot enable by them both. So essentially, not even that most of the mitigation are disabled or not enabled by default or not even available there. There is a lot of problems with them, even if you do enable them, like performance downgrade, or some of them are not supported in, for example, pay phase at all, or they're not compatible to each other. So it's not great, essentially. However, we will still encourage every vendor to carefully wait and analyze if specific mitigation couldn't be enabled in their specific software stack and their image, because it significantly can improve the state of the security software and can increase the cost of exploitability. However, for now, in practice, many of the mitigation and hardening technologies are rarely or if ever enabled at all. So if you know that mitigation technologies are not really enforced there, what about the detection technologies? Do you have any software stack like EDR or XDR or advanced threat protection software there? It's dramatically limited comparing to the available solution to the operation system. So it's not great. However, it's slowly and very slowly changing, and recently we have a new startup who trying exactly to address that gap, who will bring the visibility of the detection in the UEFI. However, are we completely lost? Because listening about all of these problems with the mitigations and vulnerabilities which we found, it doesn't look great. And some of the hope gives us the new movements to bring memory safe language to develop a critical code like Rust to develop a UEFI payload, for example. And this is a very great movement. And also it's worth to mention that NVIDIA, together with other core, they use Spark language to bring some of the benefits of memory-safe language and type-safe languages to this firmware microcode as well. And NVIDIA is rewriting many of their microcode in the Spark language. And Spark is kind of like a Rust, it's a memory-safe language, but it's also much more strict, so you don't have also arithmetic overflow problems like that. And additionally, they give you safety certification for free. So this is something which is very good, and there is some hope there. And this is also a good time that we would like to warmly thank multiple entities who help us doing this research, especially NVIDIA for supporting this research and assistant in the coordinating this disclosure, and also Intel, Red Hat, and Dell, who helps us to address multiple problems during this research, and also discover at scale potential vulnerable vendors. So thank you very much. And that's all. Do you have any questions which you can answer? Thanks.